Okay, so we can get started. Hello, everybody. Good afternoon and Happy New Year. I hope everybody had started the new year with a good start and ready to have a healthy and productive year ahead. Today, we are happy to have Shahbaz Alvi from CMCC with us to have this CMCC talk on turning data into resilience, machine learning approach to wildfire risk assessment. Before we start the webinar and I hand it over to Shahbaz, I would like to introduce briefly the CMCC Foundation and some background about the type of research we are doing here. Okay. So CMCC this last year celebrated its 20th years of establishment in the climate science, and the focus of the CMCC is climate change research dedicated to the problems in the 21st century. We are a leading research center focused on understanding the intersection between climate change and society. We have a global network of partners starting from policy related to IPCC work. As you can see in this slide, there are lots of international partners. This is just a subset of all the partners that we have throughout different projects that we have worked with, to some philanthropic and non-governmental organization. CMCC is a non-profit foundation and a charitable organization registered in the US also. Our mission is developing the models that bring solutions, advancing climate research through multidisciplinary analysis, combining climate modeling, impact assessment, and environmental economics. We are also supporting science-driven adaptation and mitigation actions. So as you can see here, the transversal and multidisciplinary research that we are doing combine first-class climate modeling with climate change impact modeling and environmental economics. Our foundation has been structured into 3 multidisciplinary research institutes, plus 4 strategic programs on frontier topics. We have a computing infrastructure dedicated exclusively to the study of climate change, and we have 2 specialized centers on digital innovation and high-level education and training. I'm gonna talk a little bit about all these centers, programs, and institutes and help you familiarize with the structure of CMCC and the research we are conducting here. As I mentioned, we have 3 main institutes within CMCC. These are our core research activities being conducted there. We have Institute for Earth System Predictions, which leverage climate modeling capabilities and turn scientific knowledge into improved predictive tools. We have an Institute for Climate Resilience, where transdisciplinary research at the intersection of climate, ecosystems, and society is conducted to support decisions, planning, and investment toward climate resilient development. Finally, we have the European Institute on Economics and the Environment, where we evaluate sustainable and socially enhancing climate strategies at the intersection of environmental technologies and the economy. Beside these 3 institutes, we have 4 cross-cutting strategic programs which shape the future of our research directions. The first program is integration of the planetary and industrial carbon cycle, trying to model carbon cycle to support the transition to low emission economy. Then we have the Global Coast as the new frontier program, where we develop digital twins to explore coastal phenomena at the intersection of physical and economic process. The third program is predicting socioeconomic outcomes in a changing climate, where we develop integrated models to support adaptation within policy and investment timeframes. Finally, we are having a very new program this year, integrating artificial intelligence and machine learning in the modeling chain, where we leverage data-driven approaches and machine learning to enhance modeling and analyzing large-scale data. Beside these 4 programs and 3 institutes, we also have 3 centers. The first center is High Performance Computing Center, where we host the most powerful computational facility in Italy and one of the most advanced one in Europe, fully dedicated to climate change research. Then we have Advanced Digital Innovation Center. This is the center where Shahbaz, our speaker today, is coming from. A transformative hub bridging cutting-edge technology with the critical research needs of the future. And lastly, we have Advanced Training and Education Center, where provides education, training, exchange, and knowledge transfer on climate change. Together, these 3 centers, 4 programs, and 3 institutes help us shape the research of the 21st century on climate change solutions and provide innovative solutions for the task that we have ahead of us. For the purpose of this talk, if you like to interact with the speaker and also ask questions, your audio and video are deactivated, but you can use the Q&A section at the bottom of your page to post Q&A questions. So I stop sharing and I will introduce our speaker today. Shahbaz Alvi has a master's degree from Stockholm University with a specialization in theoretical physics. He has a PhD from University of Ferrara in Italy with a specialization in cosmology. His core skills lie in mathematics, statistics, and numerical methods. He has been part of the Advanced Digital Innovation Center, one of our 3 centers, which is dedicated to numerical and advanced modeling methods at CMCC. He has worked here for 3 years and his research has been focused on developing artificial intelligence and machine learning methods for forecasting the fire danger index and the related risks. So we are very happy to have Shahbaz with us today. And with that, I will hand it over to Shahbaz to start his presentation. Thank you, Shahbaz.
Thank you, Soheil. So I will share my presentation. Let me share my screen. And right. So good morning, everyone. Thank you for the nice introduction, Soheil. And thank you all for taking time out for the webinar this morning. I understand I'm standing between you and your lunch, so I will try to keep it simple and not drag too long. So I'm going to talk about our recent research on data-driven approach for wildfire risk assessment and present some of the results that we have acquired in the last year. So just to give you a quick start on how we define wildfire. So basically, wildfire is an unintentional event in which fire starts in an area with burnable biomass and rips through the area in an uncontrolled fashion, potentially spreading to neighboring areas respect to where it started. And wildfires basically result from a very complex correlation between several different factors. For example, weather is an important factor, vegetation availability is an important factor. And on top of all of that, it's also important to have an ignition source that can basically start the fire. So forest fires in reality are not in per se a bad thing. They have been a part of our ecology since basically forever, because forest fires recycle nutrients, lock in the dead vegetation. They also stimulate regeneration of the vegetation. However, in the current Anthropocene era that we live in, frequently occurring forest fires, such as those caused by human intervention, have an adverse effect on the economy and ecology of a region by not only destroying the natural landscape at a higher frequency, but also spreading to human habitat and human infrastructure, disrupting economy and causing mass displacement and evacuations. And 2025 has been one of the worst years from the perspective of wildfires for several reasons. More than 1 million hectares of area was burned in the European region, resulting in the emission of about 43 million tons of carbon dioxide. While humans are not the only cause of forest fires, but over 90% of forest fires occur due to human intervention, intentionally or unintentionally. And within the European countries with a Mediterranean-like climate, these countries have always been hit hard by wildfires. But in 2025, fires have also spread to countries which are located further north, such as fire incidents in Hampshire and Isles of Wight in 2025. So forecasting the fire danger associated with wildfires serves several important purposes. On top of everything, it serves public awareness into the conditions which are susceptible for wildfires, which ultimately help reduce the occurrence of fire events by reducing the ignition probability. Early warning systems can help civil authorities train the firefighting personnel in anticipation of a fire, which is ultimately predicting forest fires is a core component of the early warning system. In the same way, distribution of resources in anticipation of fire further assists in minimizing the losses that could potentially occur due to forest fires. Then predicting the occurrence of fire is central to assessment of associated danger. If there is very low or zero probability of fire, of course, obviously there is no associated danger with it. So forecasting the fire danger for risk assessment is of course not a new idea. For decades, process-based frameworks have been used to forecast the danger associated with fires. However, these frameworks rely on processes that can be expressed analytically, such as fuel atmosphere moisture exchange based on wind conditions, etc., primarily based on weather input. For example, these process-based systems primarily use weather as an input and coupled with some physics equation to assess what is the risk or what is the danger associated with the forest fire occurrence. However, the fire occurrence is well understood to be a more complicated process, and that it involves variables which are difficult to include in process-based variables. So among these variables, the top of the list is how humans affect the probability of fire occurrence. Given the fact that human presence is highly dynamic, complex, and random, it's very difficult to include that in process-based frameworks. Second is the availability of burnable biomass. It is understood that the burnable biomass, the availability of it, the amount of it, is strongly correlated with both fire occurrence and fire severity. The probability of fire occurrence is an important component of fire danger assessment. The probability of fire occurrence on a given day is essentially a joint probability of fire predictors being in the right range, which essentially means right fire weather condition, presence of the probability of presence of ignition source, but using only a subset of these fire predictors, like it is done in process-based frameworks, can lead to a systematic overestimation of the risk associated with these fires. To understand this, imagine that on a given day, on a given location, that the weather variables and the vegetation-related variables were very conducive to fire. Thus, if you only include this information without the presence of ignition source, the fire probability is very high. But if an ignition source is not present in that location, the fire risk is essentially zero, and associated danger because the probability of occurrence is essentially zero. And this is essentially what causes the overestimation in the risk. So machine learning methods are quite common nowadays and are frequently used for a variety of different use cases. And earth sciences and climate is not an exception to that. These methods specialize in identifying underlying pattern in the input data with respect to the target variable. So machine learning methods give you an edge in predicting possible outcomes. thereby potentially overcoming the limitation of the process-based methods in predicting in the predicting power, as you can include a wide portfolio of input variables which are difficult to include in the process-based analytical frameworks. In this sense, the data-driven method replaces process-based frameworks with data-driven numerical methods. So among the large number of ways ML methods have been used, I will explain quickly to the audience the crux of how ML method works for audience which are not technically inclined towards machine learning. I will focus on the type of networks which are related to this webinar. So imagine in machine learning, there is a classifier network, which can be somewhat taught how to classify images into two or more categories. So for example, the networks assume that it is trained to classify images of cats and dogs under the label of, well, cats and dogs. And the network then basically learns the decision boundary. So you show the network a large amount of cats and dogs, and it basically the network learns to associate a decision boundary. So this is basically the decision boundary that I'm talking about. And these are basically the samples. So one of them is the cat sample and the other is the dog pictures. And this is basically the decision boundary that the network essentially learns. Then this feature space that is shown in the decision boundary is essentially shown as 2D, but of course in practice this decision boundary is this feature space is actually quite like a lot more complicated. And the decision boundary basically separates these two kind of samples, and the network basically learns to classify which side of the boundary the image belongs. So among the many ways in which machine learning methods have been applied to the problem of forecasting forest fire occurrence, one way that involves CNN type architectures. So CNN stands for a convolution neural network, which is essentially the same one that is often used to classify cats and dog images, is to extract to extract images around the fire event. And then the output of the network is the probability of the image being classified as a fire, which essentially input the probability that there is a fire on the central image. And this is interpreted as the probability of fire occurrence on the central pixel on that sample. Another variation of CNN, so this here, for example, shows you and it gives you an idea of what the sample looks like. So the central pixel has a fire or no fire. And this is the height of the sample, this is the width, and then these are the number of features. So it's basically like a 3D cube. Then another variation of the convolution neural network, the CNN, is another kind of network in which it's possible to include the time dimension. It's called the convolutional LSTM, which uses samples with an additional dimension of time, in which each sample cube is basically a 4-dimensional array. In other words, there is a 3D sample cube for every time incident. So this is the day of the fire, and there is one sample for it, then there is another one, there's another one, and this is basically one complete sample for a convolutional LSTM. And the benefit of machine learning is basically to include an extended portfolio of features that are difficult to include in process-based methods. So for example, in this method, we can introduce variables that map the human activity in the fire occurrence and their contribution in the fire occurrence, and what kind of vegetation is available, how much it is available, and you could basically include a lot more fire predictors. So the essence is basically that you train the network on two kinds of samples, which is called fire sample and is called for no fire samples. So again, for audience which are not technically aligned towards machine learning, I will say words like fire and no fire, and you will think of cats and dog images, and everything else will follow the same, basically. So you train the network on showing how a fire sample looks like, and you train the network on how the no fire sample looks like. Well, despite the high frequency of forest fires that has happened in the last decade and also in the last decades, the number of fire locations in a geographic zone is still very limited compared to the location when there was not a fire. Therefore, while fire samples can be easily picked out from the dataset, the wide distribution in the no fire samples requires some curation. Even for fire samples, some curation is often adopted, such as being selective on the land cover where the fire samples are taken from. But of course, these two samples have an overlap, so they look similar in some sense because the conditions are basically stochastic in the sense that the fire occurrence is random. So these two samples is the potential of them looking very similar. So that's why there is a strategy that needs to be adopted in order to curate the samples, in order to pick the samples correctly. So at this point, you have your favorite architecture. You choose either CNN or you choose a convolutional LSTM. And then you have a strategy for how your samples are going to be prepared to present to these networks, your fires and no fire samples. And that's fantastic. But how do you know if your model is a good predictor of fires? So several techniques have been adopted in this kind of approach in literature. So primary method to test the model performance basically is to compute the percentage of the samples in the test data set correctly labeled as fires. And this is what we call the recall. Then there is another metric which is called the precision, and which is basically the number of false alarms or false positives flagged by the model in the test data set. So suppose that the model flagged it as a fire, but in reality, it was not a fire sample, it was a no fire sample. So imagine, so basically this, you can think of it as the false alarms, that the network was very confident that there was a fire, but in fact, there was not a fire. And then the precision is basically just used to assess how many of these samples exist. Other times, a full map inference is often is created for very limited days, and it is used primarily to assess the successful detection of fires on the map. But assessment of false positive from these maps is often very limited. Then the computed full maps are often also compared with canonical indices, like for example, the Canadian Fire Weather Index, to find similarities. But it is important to understand that while some similarities are expected between these maps, they need not to be the same. They don't not to be the similar. There might be some overlaps, there might be some similarities, but don't have to be the same. There are necessarily some contrasts as well. While these standard metrics are very insightful regarding the performance of the model in predicting forest fires, in an operational scenario, these metrics are of limited scope in terms of operational performance of the model. But why do I say that? So if you follow a certain strategy for curating samples from the data set, you inadvertently confine the samples to a certain region of the complex feature space, which is high dimensional, is complex. And test samples which you curate in the same way will potentially overlap with the training samples. And this overlap is difficult to quantify or understand how much overlap it exists. This underlying overlap will estimate the model performance on test data sets because of the overlap with the training samples. So suppose the model has been trained on a certain number of samples and the test samples look too similar to the training samples. So this will essentially bias the model performance. And full map inference are performance on test data set because of the overlap with the training samples. So full map inference in this regard is operationally more useful than test scores because fundamentally it is the map that is used for differential analysis of fire danger. So you basically, if you create a model and when you serve the model to the civil authorities, essentially for them, it is important the fire danger index map so they can make the differential analysis of which parts of the region are at a high fire risk or other are at a low fire risk. So it's the full map inference from the model that actually is important. And when you actually make this full map inference, the model encounters the full distribution from the feature space, not only those bound by your sampling strategy. So in this work, we propose a framework which assesses the real world performance of a model in predicting forest fires on an operational level. So we propose that the full map inference should be the primary method of assessing model performance rather than the test data set. The daily recall is computed directly from the full map inference, not from the test data set. False positives are assessed directly from the full map inference, and that the false positives are operationally as important as having a high recall. So having low false positive is as important as correctly detecting the fires. And training an ensemble of model for forest fire prediction and aggregating them has a more robust performance than individual models. So now I will basically try to demonstrate our how our proposed framework works in our setup, which is basically the same setup which is adopted in the work that I cite in the slide. The target geographic region is the Mediterranean region, basically around Greece, which includes Albania, some parts of Western Turkey, for example. And the data set is comprised of 13 years of historical fires, their location and their date, and the fire drivers, which are used in the cited literature. The architecture that we explore in this work is the CNN and the convolutional STM. And the network output is the probability of samples being classified as fire, which is interpreted as the probability of forest fires on that location, which is called the fire danger index on that location, or in short, the FDI. So one quick word about the fire drivers. We essentially use the same fire drivers which were adopted in the literature that I cited. And you can clearly see that there is a much wider portfolio of fire predictors that we can adopt in this kind. We have adopted in this kind of world. So imagine that for a process-based method, your most of the fire predictors are basically in this category, which are weather. But with machine learning methods and data-driven methods in general, you can adopt a lot more fire predictors into your analysis. So how we curate our fire samples, our no fire samples, or as I was saying, our cats and dog images. So for fire samples, we choose the fire samples from land cover where the fires occurred more frequently. And this distribution is shown in the plot in the orange. So these are the land cover. These are these land covers from where the fire distribution is coming from, has been drawn from. And they are basically shown in orange in this plot. So in a given year, fire samples have unique locations. Then we do not restrict the model to only fire samples in the fire season to not make the model too strict in terms of the feature space. In the data set, there are almost 10,000 times the no fire samples than there are the fire samples. So there is a very huge distribution. So in the data set, there was something like 25 or 26,000 fires. So imagine the no fire samples are 10,000 times this number. So it requires a bit more consideration how a no fire sample is chosen. Essentially, you don't want the no fire samples to be too similar to the fire samples, neither too distinct. We choose no fire samples from the fire season in a given year. Then, to not make the no fire samples too similar to the fire samples, we choose them from days when there were no fires in the region, in the target region. We choose them from land cover classes, which are theoretically susceptible to fire, even if no fires were found on those land covers in the data set. Then locations which have already been chosen as fire samples in a given year are ignored. So no fire samples are chosen from locations where there already have been a fire sample. And finally, to balance the data set to not have too many fires or too many no fires, we choose basically 2 times the no fire samples compared to the fire samples. So the network is trained on a balanced data set. We considered 4 different kind of architectures. One is what we call the basic CNN, which is one convolutional block, one classifier block, very simple, very vanilla CNN. Then we choose a deeper CNN, which has 3 convolutional blocks and 1 classifier block. The third is a deeper CNN2, and it's a 4 convolutional block and 1 classifier block. So when you add more convolution blocks, you basically add depth to the network. You add complexity to the network. Then we have the convolution LSTM, which is 1 LSTM block, 1 convolutional block, and 1 classifier block. The best model that we use eventually for inference, for doing the analysis, for getting the fire danger index map and the prediction is the one where the validation loss is the mean, is the least. So here in the table, I use the standard way how machine learning methods are tested. I do the test data set and I compute the recall, precision, and another metric called F1, which is the balance between precision and recall. And there are several interesting things that you can see here. In the table, we see that the F1 score is essentially the same, which basically is a balance between these two. Between all 3 networks, you have F1 score is the same, even though you can see that the convolution neural networks, the CNN type architectures perform slightly better than the convolution LSTM. And this is what you can see also in the percentage of fires correctly recalled, and also in precision that convolution LSTM performs slightly worse than the CNN architectures. So following our proposal, what we do is that we choose the fire season in 2020 and 2021, which is the total of 149 days. And we compute the full map inference of the entire region on these 149 days. Then for each day, we identify how many fires were correctly recognized in the map compared to how many fires were actually there. So we compute the recall directly from the map. And this result is summarized into this Q quantile table of the recall. So effectively, the Q quantile shows the percentage of days on which the recall was less than the reported number. So if I say that this number for basic CNN, the 40% Q quantile is 0.74, it means that 40% of the days the recall was 0.74 or less than 0.74. So from the table, it is evident that the convolutional LSTM outperforms all other architectures, as it can detect more than 90% of the fires on more than half of the days in the fire season, and has a perfect score on 40% of the days. Another interesting factor that you can see is that the CNN type architectures, all three of them, basically perform more or less the same on all of on the entire data set. So increasing complexity of the CNN does not appreciably change the performance in fire recognition. So before moving on to the next aspect of the evaluation framework, I want to quickly show a comparison of the fire danger index computed by the convolutional LSTM and that compared with the Canadian Fire Weather Index, which is computed on the same day. So comparing the maps, three things becomes very clear. The fire danger index from convolutional LSTM has significantly less false positives than the Canadian Fire Weather Index, given the fires that occurred on the day, which are marked by the icon. So you can see these icons, which are identifying the fire locations on those days. So you can clearly see regions like this, where there is essentially no fires, but the fire weather index is quite high, and machine learning method with convolutional LSTM can significantly reduce the number of false positives here. Then you can see also similar trends in this part of the map here. The second is that while there are similarities between the maps, there are also subtle differences between the maps. That is, the map produced by convolutional LSTM tracks more accurately the fire activity that occurred on that given day. And while there are similarities between these two maps, one can also appreciate the contrast between these two maps. So imagine that in convolutional LSTM, a data-driven method directly tracks the fire activity, while Canadian Fire Weather Index basically tracks the fire weather conducive to the fire occurrence rather than directly the fire activity. Then moving on, from operational point of view, as I was saying, that rejecting false positives, which means lesser false alarms, is as important as detecting fires. So imagine a map of fire danger index where every pixel is recognized as a high probability of fire. Well, it essentially means that on that day, every fire will be detected with a very high confidence. But of course, a map in which all the regions are at a high fire danger, such map cannot be very useful for differential analysis on an operational grounds on how fire weather index changes from one region to another region. And thus, it would not be possible to organize resources for such a distribution because everywhere there is a high fire danger index. So to analyze the ability of the model to flag false positives, we select 6 days at random from the fire season in 2020 and 2021, where no fires had occurred. And this is a more meaningful assessment of the false positives generated by the model, because there were no fires occurred on that day. So every region at high fire risk is basically a false positive. Then we plot the distribution of the fire danger index values on each day for each of the architecture considered. And the network distribution is more, and the network with the distribution which is more negatively skewed is an indicator of lower false positives compared to another network which has a positively skewed distribution towards higher values of fire danger index. And from the bar plot, one can see that convolutional LSTM has the most negatively skewed fire danger index distribution compared to the CNN architectures. And furthermore, this is something you can also see in the full map inferences, which are basically shown in this plot, that the maps from the convolutional LSTM have significantly less noise than the other CNN architectures. Another interesting in inference that you can make from the map is basically that among the CNN architectures, the deeper CNN has the optimal network depth to perform best in terms of false positive alarms. So you can see that the distribution that the in deeper CNN1, the distribution is more negatively skewed compared to the deeper CNN2. So it basically shows that the deeper CNN has the optimal network complexity or network depth to correctly identify the false positives. In this correctly identify and reduce the false positives compared to a deeper CNN. So there is an optimal network depth, which is a very standard inference and standard result in this kind of approach for convolutional LSTM for the convolutional neural networks. Then moving on to the last aspect of the framework that we propose. Well, ensemble-based approaches have been very widely used for several important use cases in where machine learning has been used. So we asked the question: can we take an ensemble of machine learning models for fire danger index fire danger index, and then this ensemble can it perform better than individual models? So what we do is that we basically take 7 members in each ensemble. And the architecture is a convolutional STM because that has the best performance. The differences between these ensemble members is how the weights are initialized. So imagine that each network starts from a random point and it tries to basically optimize and find the least loss within that area. So each of the models are basically initialized with random weights. Then the FDI map from each of the ensemble is basically averaged over the entire ensemble to basically create a new map. And what we actually get from this. So we apply our assessment framework to compute the full map inference from each ensemble member and each day of August 2020, which is the month randomly chosen. To formalize, imagine that this theta is basically a noisy estimator. Is basically a noisy estimator. Sorry, this theta here without the cap is basically the true latent fire danger index on that day. We call it latent because fire danger index is not something that you can measure, or it's not something that you can compute directly from other variables. So it's something that you don't know exactly. But when you train a machine learning model, or even when you use a fire weather index, you're basically creating an estimator which you want to very closely mimic the true latent fire danger index. So each ensemble member is essentially a noisy estimator of this theta. And each ensemble is what we recognize as this theta cap, and T is basically 1 day. Then what we do is that we basically take each ensemble member and we compute the fire danger index, and we create the full map, and we compute the recall from each of the day in August 2020 for each of the ensemble, and the result is shown here in this heat map plot. And from the plot, one sees that the average recall from each of the ensemble is equal to the recall computed with the ensemble average of the FDI map. So essentially, this is true. So if you basically average over the ensemble and then compute the recall for each day, it's approximately equal to computing the recall on each ensemble and then averaging it. And given that the recall is essentially a nonlinear function, this is not a trivial property that is obvious to this kind of approach or this kind of problem. So looking at from this result, this equality, this approximate equality, there are several interesting inferences that follow. One is that ensemble members make similar estimate of fires and no fires on the map. So there are no systematic bias in the fire danger index, only random noises. Most models are quite good at detecting the high number of fires on each day. So there is a high recall by most of the ensemble members on most of the days, which is indicated by all these ones, which basically means 100% of the fires were detected on those days. Then, as most ensemble members roughly make the same estimate of fires, one can say that most models make confident estimate of fires. That is, they are far from the decision from the decision threshold. So the model is basically predicting a very high confidence in fire location, even if there was no fire at that location. Generally, the recall from ensemble average FDI is more robust than the randomly selected model from the ensemble. So if you take the average of the map computed by all the ensemble, that has a more robust recall rather than each of the ensemble members individually. If you pick an ensemble member randomly, then the recall is generally less robust than those by an ensemble average. And then we do the same analysis that we basically take the days when there were no fires detected in the entire region. And we take 6 random days, and we basically plot the distribution of the fire danger index values for each day on each ensemble on these randomly selected days. One can see that generally in the ensemble average map, there is a lower number of false positives because the average map, the distribution is more skewed, is more negatively skewed than some of the ensemble members, like this one. So not only the ensemble average is robust in terms of correctly recognizing fire, it's also robust in reducing the false alarms by skewing the distribution of the FDI values towards lower values of FDI. Then we arrive at the conclusion, and we say that basically, just to sum things up, ML-based methods can dramatically reduce false alarms compared to canonical indices, thanks to the additional fire predictors that can be included in this analysis, in this kind of data-driven analysis. A standard method of evaluating the performance of ML classifier might be biased and less comprehensive for operational forecasting of daily fire danger index, because as I was saying, from an operational point of view, is the full map inference that is what really matters. Evaluating recall and false positive on full map inference offers a more comprehensive measure of a model's operational performance for daily fire danger index forecast. Then convolutional LSTM offers the best performance both in recognizing fires and reducing false positives. Then for a CNN, there exists an optimal complexity that minimizes the false positives. And the average over an ensemble of convolutional LSTM models generally improves recall and reduces false positives. And before I finish, I just want to quickly publicize this paper, which basically on which this presentation was based, on which we have highlighted our work. We basically examine in more detail some of the results. There are more interesting arguments, more interesting results that we included in the paper, which were not possible due to time restriction. And the paper is very soon going to be available on arXiv, so you can have a look at that to get a deeper idea of how we perform this analysis. And I will stop here. If you have any questions, if you have any curiosities, feel free to ask.
Yeah, thank you very much, Shahbaz. Very, very interesting presentation. So, as I mentioned earlier, the audience can use Q&A section of the platform. It's at the bottom. It says Q&A. Please feel free to post questions there, and we will share it with Shahbaz as they come. So, Shahbaz, maybe I will start the discussion a little bit about the factors that you talk about. You emphasized on some of the limitations of the process-based models, that they don't include, for example, human activity factors, and moving to machine learning, those factors can be included. So can you talk a little bit about these examples that you showed, what kind of factors you included in the fire risk index, and how did you gather the data for those factors?
Right. Okay. So, as I was pointing out, that basically the data, the fire predictors, the fire location, all of that were basically followed by the reference that I pointed out, which is basically this one here. And the authors actually did a really good job in collecting the historical fire data. They also harmonized it, and they also basically included the fire predictors, which were used in the work. We essentially followed the same. So we essentially took the same fire variables that the authors took, because the analysis of the authors did already included why these variables are important for the fire prediction. So we essentially retained the same fire predictors which were used by the authors, and we only basically extended on the validation part, basically.
Yeah, thank you. So we have one question in the chat. It talks about, so I can read it. Thank you for the presentation. Not a specialist on machine learning here, but I have a question regarding the choice of the lower number of the no fire days. Is it possible that the over prediction for the number of fire days is because it considered the ratio of fire to no fire days to be much higher than reality based on the number of samples provided? It seems like the model is using something like a binomial distribution plus the ensemble averaging to reduce false positives instead of directly using a Poisson distribution to describe the probability. Is it something like that?
Okay, so that's actually a pretty good question. That's actually let's suppose like it's more like a question of how to optimize it. So the idea is to choose the two times the no fire samples. You basically, when you choose the no fire, so to start things, fire samples are somewhat easier to choose because you already know that there was a fire there, right? So you basically do very minimal curation, but you basically pick those numbers, pick those samples. But no fire samples require a little bit of a thought, and for several reasons. First of all, you don't want the fire samples. So if you choose, for example, the same number of no fire samples and the fire samples, since there is a very wide distribution of the no fire samples, you want to be able to make the sample as wide as possible in terms of distribution. But at the same time, you don't want to have five times the number of fire samples because it also imbalances the data set. The network is more trained to know fire samples than fire samples, which essentially will tip the network performance into missing fire samples, like fire events, and actually flagging more and actually having more false alarms. Lesser recall. So it will not be able to recall fires correctly because you tilted the balance. Then another thing that is very peculiar about about applying machine learning methods to the fire danger index problem is basically that when you have a false positive, that's not exactly a false positive. That's basically a fire alarm. So when you have a high fire danger index in some region, then it doesn't necessarily mean that there's actually going to be a fire, because fire occurrence is a pretty stochastic process. Um, so when you have a false positive, you actually want to have some false positives, because a false positive means that there is a high probability of fire occurrence. Whether fire occurs there or not is a random process. So what you want, of course, I mean, so what you really want is not to have too many no fire too many false alarms, because if you have too many false alarms on your map, then effectively that is operationally not very useful, because you cannot differentiate where to allocate the resources, and essentially the entire map is basically red. So the consideration for two times no fire samples, as it was done in the literature that I've cited, is to basically balance between this performance metric. And unfortunately, there really is no strict recipe. There have been some researches where people chose the same number of fire samples, 1.5 times the fire samples, or three times the fire samples. So it's something that is not entirely, there's no strict recipe to how to choose this. How we did this in this how we make this choice in this work was based on operational performance. We did perform some other network training where you had different number of no fire samples than fire samples, and we basically optimized this number based on a balance between recall and the false positives.
And just quickly, we have a couple of questions, but follow up on that. I think there was also a point about the days you chose. Did you
Exactly.
choose the days with the fire incidents or the days that were no fires?
Yeah, exactly. So the no fire samples were basically taken from days. So what we did for every year. So for on each year, we define a fire season, and fire season is defined in this way: the date on which the first fire occurred in that year and the date on which the last fire occurred in that year. And then this is what we define as a fire season. They're not the standard fire season that is usually July, August, and September, the Mediterranean region. This is what we define as a fire season. Then the no fire samples are always within this stage, within this season, and within this season we want to have a sample similar to the fire but not too similar. So we still chose the days where there were no fires detected in that region, and this basically gives us a balance between having a day where the conditions were very good for fires but fires did not occur anyways. So we still give some sort of it's more like balancing the similarity between fire samples and no fire samples, but not being too similar or too contrast.
Yeah. So on this, the graph now you are showing, there is a question about the weighting of different factors. What are the weights? How did you compare or include different factors with different weights?
So these factors in terms of weights are all weighted in the same way. We basically let machine learning method, the architecture, the net training process decide which of these factors are more important for fire occurrence, which are not. We, as per se, don't put any specific weights on any of these variables.
Okay, great. And in terms of application, you showed a region like a South Mediterranean region. Are these kind of your model? What level of applicability it has? Like it should be a small region or it can be like a global kind of application?
Okay, so since the model is trained on, and that's actually is an excellent question. I mean, whoever asked that, I mean, I really thank you for asking this question. That's actually is the question ties in more on the extrapolation of the model. In principle, the model is trained on Mediterranean region. So we have had some applications in some work where the model was applied to other Mediterranean region, which are outside this geography, within this outside the geographic zone. And we had some limited, well, not limited, but we had actually decent success in being able to correctly identify fires. So I could say with the decent level of confidence that a model which is trained on the Mediterranean region is generally, at least in our analysis, was extrapolatable to other Mediterranean region like Italy or Portugal. But to say the model can be applied globally, that is, I would be apprehensive in making such a claim because you are basically extrapolating the model too far away from the region where it was trained. So imagine that, of course, when you take a Mediterranean-like climate, the fire season, which is Mediterranean-like, the correlations between these variables are somewhat fine-tuned in some sense on this region. To say that the same applies to India or Pakistan or other places, like for example the US, that would, I mean, it would require some tests to understand how much of that is true. And that's is an open area. It's basically an open question of research. It's not easy to answer.
And there is a question about this conv LSTM. Is it run on the cloud or is it run on the local, basically, infrastructure?
Well, for this, I mean, so the convolution LSTM model is basically was also the same one that the authors of this paper use. It's basically the same convolution LSTM that they use. We just basically used it as it is without any alteration. And and their code is also publicly available. So basically, we just use their model, and for training and for all these evaluations, we use the CMCC's the high performance computer center to do all this analysis.
Yeah. There's a question about when you, at the beginning, your introduction, you mentioned that most of the fires are basically created through the human intervention, like the wildfires we know. And but then it seems that when you were showing the results, basically the model, the Convel STM, shows maximum convergence when it is basically the environmental conditions are matched, if I'm not mistaken, or if I can rephrase the question correctly. Um, is it something that you can comment on, or I can read the question also as it is? As you indicated, 90% of the fire events are man-made, and your scale of Convel STM shows maximum scale when condition is 60% or above. How the model is dealing with it.
So when I say that most of the fires are 90% of the fires were caused by human intervention, that's not a result that was driven from the network itself. That was the statistics which were reported by the civil protection authorities. So it's not something which is a result of the from the work itself. It's basically the fire incidents which were reported and investigated to be found that the source of the ignition was a human factor.
Great. So maybe I just read the other one. Thank you very much for the presentation. In addition to the variables mentioned, have you tried including live fuel moisture in the fire prediction models? How was your experience? You mentioned this variable on one of the slides at the beginning of the presentation.
Right. So no, that is not included as one of the variables. I know that there have been a very interesting work that included the same variable with very interesting result. But the focus of this work was basically more on model evaluation. So we did not so much experiment with different kind of variables that you could include. But I do know that that variable has been included in some work with very interesting results.
Okay, and we have the last question. Traditional fire danger indices rely mainly on meteorology and vegetation. How does your machine learning based FDI avoid over relying on vegetation proxies and instead distinguish human driven ignition from purely climate driven fire risk?
Yeah, that's actually a nice question. That is more a question of feature importance rather than the results that are shown in the analysis here. A lot of the work, I mean, even the paper that we have cited here, they did actually do an analysis of feature importance of which of the if there's a weather variable which is more important, or if it's a vegetation variable which is more important. Definitely, I mean, both of them have a high relevance with respect to the fire occurrence. If I remember the results correctly, the weather variables had a higher yeah, if I remember correctly, the weather variables had higher relevance than the vegetation, but they were comparable. Not a significant contrast between between the relevance of these two variables.
Okay, thank you very much, Shahbaz, for a great presentation and everybody for a very interactive and interesting discussion. I just close by mentioning that we have a working group across CMCC, different divisions and institutes have been involved in researching fire and issues related to climate change, impacts on the fire risk and so on. And we are working together within CMCC across different groups. And if you are interested in the work that we are performing, please reach out to us, to Shahbaz, to me. I am directing the program on the carbon cycle, and we will be happy also to expand our network of collaboration. So happy to hear from you, and thank you very much for attending this talk. Have a good rest of your day. Bye.
Thank you, everyone. Have a nice day.